All right, great. Thanks very much. And thank you all for coming today. It's a great pleasure to be here in Riverside. It's been a wonderful visit so far, and I look forward to having a chance to talk to you all for the next hour or so. So I have sort of a funny title, Is Nature Natural? And at the very least, by the end of the talk, hopefully you will agree with me that it's an interesting question to ask. Whether or not you think the answers that I would like to suggest to it are useful is entirely up to you. So I should, of course, start with a caveat. Anytime you start a talk or anything else with a question, at least in high-energy physics, we have something called Hinchley's rule, which is the assertion that whenever at least the title of a paper is a question with a yes-no answer, the answer is always no. So at least by Hinchley's rule, trivially, you can draw conclusions about my talk. But my conjecture is that talks should be exempt from this rule. OK, all right, that's my obligatory joke. So it's been an exciting time to be a high-energy physicist. I'm a theorist, but I think also this is true for my colleagues who work in high-energy experiment. In the last 5 years, of course, have been marked by the discovery of the Higgs boson at the LHC, by the ATLAS and CMS collaborations, and by the ongoing effort over the last 5 years to understand what that discovery actually means and what are the properties of the particle that we've discovered. So I chose this nice New York Times snippet as an exemplar of the discovery just because Dennis Overby is not that effusive of a person. So when he writes a headline like physicists find elusive particle seen as key to universe, you know that something significant is going on. So why was the Higgs discovery so important? Why has it been so central to thinking about theoretical and experimental physics over the last 5 years? Well, this is a story that most everyone knows, but it's worth reminding ourselves. We had, for the better part of half of a century, this beautiful construction called the Standard Model of particle physics. And the Standard Model, prior to the discovery of the Higgs, consisted of the things that we had seen in nature simply by colliding particles together at higher and higher energies, and also relationships between them that were dictated by the fundamental structure of the theory. So unfortunately, I guess the bottom of the slides are cut off. But just a little bit of lingo in case you're not a high-energy physicist or condensed matter theorist. In the language of high-energy physics, the fundamental objects, of course, in our universe are quantum fields. Excitations of those fields are particles. So sometimes if you hear me say field or particle, I'm just going back and forth between the building blocks of nature. The other thing that's important, of course, in describing the fundamental physics at high energies is the idea that the fundamental forces that we see are mediated by force-carrying particles. And those things are actually equivalent to local symmetries of space-time. So your ability to make local symmetry transformations of fields at different places, that actually has a one-to-one correspondence with fundamental forces in nature. So sometimes I'll use fundamental symmetries, and sometimes I'll use forces, but I'm still talking about the same thing. So the Standard Model, it just consisted of all of the things that we had seen experimentally by looking in nature. So that included a bunch of different quark-like fields and a bunch of different lepton-like fields, including in the quarks, the constituents of the proton and the neutron, including in the lepton-like fields, things like the electron and the muon, and then a variety of force-carrying particles that stitched them all together. So it included the gluons, which were the force carriers of the strong interactions. It included the photon, of course, which is the force carrier of electromagnetism. And then the W and Z bosons, which are the mediators of the weak nuclear interactions. And so the Standard Model was immensely successful in the sense that it had about 20 free parameters, but there were many, many more observations that we could make that depended on those parameters. And so that gave us a wide number of predictions. And the vast number of predictions that we could make in the Standard Model all turned out to agree with astonishing precision to what we were able to fix using those 20 parameters. So that was the sense in which the Standard Model has been this beautifully successful description of nature. But there was really an essential problem that troubled us from the very founding of the Standard Model all the way up until the discovery of the Higgs, which is that, of course, we look in nature and we see that all of these particles have mass, with the exception of the photon and, to some extent, the exception of the gluon. But the fundamental symmetries, the actual structure that stitches the Standard Model together and makes successful predictions, that structure actually prevents us from writing down mass terms for all of these different fields. So there was a funny, interesting tension that we see massive particles, but the very structure of this theory that was so successful actually forbade us from adding that to our fundamental theory. And if you wanted to just go ahead and steamroll the theory and add a mass parameter for these different particles by hand, you actually found that things started to go wrong at the quantum level. We said that there were problems with unitarity of the theory at high energies. That just means that as you probe the theory at higher and higher energies, probability stopped being conserved. OK, so this was really a fundamental problem with the theory. Of course, even from the early days of the Standard Model, we had a conjectured solution to it. That conjectured solution is partially cut off down here. But the conjectured solution is, of course, there's an additional ingredient in the theory. So in addition to the particles and interactions that we see, there's some other field. It's a scalar field, so it has no direct field that's valued everywhere in space, but just with a number, not with a direction. And that field, in addition to the excitations of that field corresponding to a particle that we could see, that field also had a non-zero value everywhere in space. So it had what we called a vacuum expectation value. And that vacuum expectation value, all the particles in the Standard Model coupling to the Higgs, they couple to that background value. And that background value, that energy density, looks like a mass from the perspective of the other ingredients of the Standard Model. So by adding a particle to the theory and having it acquire this background expectation value, you could reconcile the fundamental symmetries of the theory that made it predictive with the fact that we see masses for all of these particles. Okay. So from the earliest days of the Standard Model, it was conjectured that such an ingredient had to exist. But it wasn't until 2012 that we actually saw evidence that this mechanism was actually realized in nature. Okay. So that's the sense, I mean, Dennis' overview is being effusive, but really the Higgs is, in some sense, certainly the key to the Standard Model. And to the extent that the Standard Model describes 3 of the 4 fundamental forces, it really does seem to be the key to understanding everything. Now, there wasn't just a unique way, actually, of reconciling the symmetry structure of the Standard Model with the observed masses of particles. You could have actually done that in a variety of different ways. Some of them could have involved having multiple different Higgs particles that conspired in different ways to do that effect. But there are also other ways that involved, for example, strong dynamics that are analogous in some sense to QCD. So it wasn't actually obvious, if you wanted to reconcile the force structure of the Standard Model with the masses of particles, that you needed something that was just a single Higgs field. It could have been a much more elaborate mechanism. But in the context of the Standard Model, if you just add one new ingredient, if you just add this Higgs field, the simplest possible way of reconciling the structure of the interactions with the observed masses of particles, that actually turns out to be extremely predictive. And the reason is you've just added one new ingredient. If the background value, that vacuum expectation value of the Higgs, gives the mass to all the particles that couple to it, then that means you actually also can predict exactly the coupling of all the particles in the Standard Model to the physical Higgs particles, just because that coupling has to be proportional to the mass of the other Standard Model particles. So therefore, once you actually know that there's a physical Higgs and you know its mass, you can exactly predict the coupling of that particle to all particles in the Standard Model under the hypothesis that it is, in fact, the single Higgs boson. And then if there are any deviations from those predictions, you know immediately there's something else that was not included in this picture of the Standard Model. Okay. So the game at the LHC over the last 5 years has largely been to take this particle that we discovered in 2012, to interrogate it in as many ways as we possibly can, and to look for evidence that either its properties are exactly like we predict from the Standard Model, or that there are deviations that would be a sign that, in fact, there's some different underlying structure that we don't yet understand. So the story so far has been good for people who like the Standard Model. That is to say, there have been many different measurements of the production and decay modes of the Higgs boson at the LHC over the last 5 years. These are sort of some nice summaries of them. So this is a combination of data from both ATLAS and CMS from the first run of the LHC. This data should soon be superseded by measurements that are ongoing now. But what this shows you is, for example, a measurement of the rate of the production of the Higgs and a decay into pairs of Z bosons, or the ratio of certain production modes relative to other production modes. And in the Standard Model, you have precise predictions for all of these quantities, and that corresponds to this dotted line. And so then you can go and make measurements in all the different channels and ask if your measurements actually agree with the predictions. And what we see is, to astonishing precision, at least the precision that we have currently, that all of the experimental observations we make do line up, at least within 2 standard deviations. There are some measurements that have a little bit of pull relative to the Standard Model prediction, but the current lesson we have so far is there's fairly good agreement with Standard Model predictions. And if you were to sort of ask generically what's the precision of the agreement is about good to about 1 part in 5. So the precision with which we know that it's a Standard Model like Higgs, that appears to agree to about 20%. Okay. So this gives us a lot of confidence that we've in fact completed the Standard Model, that we found not only all of these ingredients, the fermion fields and the gauge, the force carriers of the Standard Model, but also this key ingredient that is responsible for imbuing mass to all of the particles. So the question is, for someone like me who works on physics beyond the Standard Model, is that it? Am I done? Do I get to go home? Or is there more to do, right? So we've completed the Standard Model. We now have this structure. We've seen all the ingredients that have to exist in the theory for it to be consistent. And all the evidence we have so far about the Higgs is that it is just one elementary extra degree of freedom. OK. But there are really two things once you have the standard model in hand. There are two things that push you to look beyond the standard model. So the first one is just to understand the actual parameters of the theory that you see. So the standard model is a theory with about 23 parameters that you can't predict from first principles. In the standard model, they're simply things that you measure and use to make other predictions. But those numbers, they vary across a wide range. The dimensionless couplings in the standard model vary over more than 5 orders of magnitude, for example. And so you'd like to understand in a fundamental theory of nature, where did those numbers actually come from? So to a certain extent, this sounds like just so stories. You know, why did the leopard get its spots? Why did the standard model have this coupling and that coupling? But they're nonetheless interesting questions for reasons that I'll try to convince you in the next few minutes. There's also another reason to be excited think about physics beyond the standard model, and that is that there actually are things that we see in nature that cannot be fit into the standard model. So of course, there's gravity. Gravity is something that by construction we exclude from what we mean by the standard model. But gravity is a very complicated object, and the theory at which quantum effects in gravity become important is well beyond the energy scale of the standard model. But even beyond that, even setting aside quantum gravity, we have two other things that simply can't be fit into the standard model that we know are out there in nature. So one of them, of course, is dark matter, for which we have gravitational evidence by looking not just at the rotation curves of galaxies, but also in constructing our concordance cosmology of the early universe. We know that there has to be a large matter component that gravitates but is non-baryonic. So that's out there and is not an ingredient that can be explained in the standard model. And we also know that the neutrinos that are ingredients of the standard model, neutrinos have mass. And in the context of the standard model as we define it, there's no ability to actually write down a mass. Even once you've included the Higgs boson, the symmetry structure of the standard model prevents you from giving the neutrinos a mass just by coupling directly to the Higgs. So those are two things that tell us that although the standard model is profoundly successful, there are ingredients that it does not include, and therefore we have to look beyond the standard model. But what I want to talk about mostly today, all right, dark matter and neutrino masses are profoundly interesting, and there's been a lot of progress on those questions here at Riverside. But what I want to talk about more today is the class of things that sort of fall more into the just so stories, namely, what is the underlying origin of all of these different parameters that we see in the standard model? Now, you might just say that's a silly question. There are lots of parameters that we see in nature that don't have some profound underlying cause, or they don't have some profound underlying meaning. For example, the distance between the Earth and the sun, that's just a number that just comes out at the end of the day. The number itself has no intrinsic meaning. It's a number that actually comes out once you understand Newtonian gravity and just the kinematic features of the sun and its planets. So we know some parameters we see in nature are not fundamental or interesting ones that we would want to explain. So you might not think that it's an interesting game to try to explain the parameters of the standard model. But what makes it a very interesting game is that the standard model, it's a quantum field theory. It's an intrinsically quantum object. And in quantum field theory, it's actually very hard to construct lots of different numbers that are very different from each other. All right, so the essential reason for this, the basic reason, is what we often call the totalitarian principle, namely that everything that is not forbidden is compulsory. So the justification for the totalitarian principle is usually something like just the structure of quantum mechanics, for example, the double slit experiment. The fact is we know that in a quantum process, we probe all possible trajectories. So if something is allowed by the structure of the theory, it's compulsory, and in fact, it must contribute to physical processes. That's sort of a facile way of understanding the totalitarian principle. More deeply, in a quantum field theory, what happens is if you look at the fields that describe your physics at low energies, they, of course, couple to the vacuum fluctuations of all of the other particles and ingredients in your theory. And by coupling to those vacuum fluctuations, they actually become sensitive to all of the other mass scales and all of the other couplings that exist in the fundamental underlying theory, even if those mass scales and couplings exist at much shorter distances. So for example, if I have a theory that consists of a light particle, and there's a much heavier particle somewhere in my theory, quantum fluctuations will actually tell the light particle about the existence of the heavy particle, and that tends to draw the mass scale of the light particle closer to the heavier one. Similarly, if I have dimensionless couplings, I can actually look at what the vacuum corrections to those dimensionless couplings look like. And what they do is they give contributions that are proportional to all of the other couplings in the theory. So in the same way, that tends to pull couplings together. So the very naive expectation from quantum field theory is not that you can just have some widely separated values of dimensionless couplings or mass parameters, but rather, generically, all couplings have the same value after quantum effects are taken into account, namely 1 in natural units. And all scales are the same. So in particular, they should all be whichever scale is biggest, because smaller scales will start to probe the bigger scale and therefore be pulled up to that higher scale. So this is a particular problem from the perspective of the Standard Model, because the scale at which quantum gravity becomes strongly coupled is 10 to the 19 giga-electron volts. That's 19 orders of magnitude. Well, it's 17 orders of magnitude than the mass scale of the Higgs boson in the electroweak scale. And so it's very hard to understand, very naively, given this expectation, why we see the Higgs at such a low scale compared to more fundamental scales in the theory. So that's just a general expectation. We've actually sharpened this criteria in high-energy physics into a pair of naturalness criteria that simply try to make sharp this expectation that in quantum field theory, dimensionless parameters are pulled together and dimensionful parameters are pulled together. So the precise framing of that is a criteria that I call Dirac naturalness. And it's just the idea that if you have some theory where the fundamental highest energy scale is something we call lambda, then anytime I have some operator in my theory or some interactions in my theory, the value of that, if it has some mass dimension, the value of the mass dimension should be the fundamental scale itself. And if it has a dimensionless coupling associated with it, the dimensionless coupling has to be 1. And this is the natural expectation that you have just from thinking about quantum field theory. But it's also borne out countless times whenever you look at quantum field theories as we encounter them in nature, or whenever you simulate them, for example, on the lattice. Now, if that were it, you would just go ahead and conclude that nature is not particularly natural, because we do see parameters, for example, in the Standard Model, that are widely separated that don't appear to satisfy this expectation. So for example, the couplings of various particles in the Standard Model to the Higgs, those range over 5 orders of magnitude. Those obviously are not all equal to 1, or even within an order of magnitude of 1. So you might naively conclude that this principle is just badly violated. Thankfully, 't Hooft understood this idea a little bit more deeply and gave us a nice refinement of the principle, which I'll call technical naturalness. And the idea of technical naturalness is, OK, the idea that all dimensionless couplings are 1 and all dimensionful scales are the fundamental scale, this just comes from thinking about how quantum corrections link scales and couplings. But there's a further refinement, and that is we know that quantum effects always respect the underlying symmetries of a theory. If there's a symmetry of nature that sets a quantity equal to 0, quantum effects will not make it different from 0. Quantum effects will continue to respect the symmetry. So we actually now can have a way of understanding why there might be parameters, that, say dimensionless parameters, that are different from 1. If I have a parameter, when I take it to 0, if there's a larger symmetry of the theory, if the theory becomes more symmetric, then if I take it away from 0 by a small amount, quantum corrections have to be proportional to that small amount. All right? That's because in the limit that the correction goes to 0, the quantum corrections are 0. So as I go by 0 away from 0 by a small amount, the quantum corrections have to be proportional from that departure. OK. So I can have a parameter much smaller than 1 if when I take it to 0, the theory is more symmetric. And this is the principle of technical naturalness. Now, if you see a technically natural parameter in nature, one that is very small, different from 1, but there's a symmetry when I take it to 0, you still have to do the work of explaining why it's the particular number it is and not some other number. But that's not as challenging of a question, right? You can at least understand it's OK from the level of quantum field theory for that parameter to be small. OK. So we go out in nature, and we actually see this borne out in many beautiful ways. So this is actually a fantastic way to understand the structure of physical parameters that we see in nature. So the best example of Dirac naturalness is actually the answer to the question that Dirac himself posed. He, of course, didn't understand the answer to the question at the time. He came up with a much worse answer. But now we have the benefit in hindsight of understanding the answer to Dirac's question. So Dirac knew only a couple of fundamental scales. He knew the mass scale of the proton, and he knew the apparent scale associated with gravity. And he asked, why is the mass of the proton 19 orders of magnitude less than the mass scale associated with gravity? OK. So the answer, as we now understand it, is actually the theory of the strong interactions. So the theory of strong interactions, what happens is you can think of defining the theory at the scale of quantum gravity, up at the Planck scale. And at that scale, there's a coupling constant associated with the strong interactions that can be order 1. And what happens as you go to lower and lower energies, or longer and longer distances, is that coupling gets larger and larger logarithmically. All right, so that's logarithmic growth is a very slow growth in some sense. But if you have a logarithmic evolution of a coupling as you go down in energies, eventually that coupling will grow large, and it will give you a new scale. and that scale will be exponentially related to the original scale at which you define the theory. So particularly in QCD, the strong interactions grow strong at a scale lambda QCD, which is approximately 1/4 of the proton mass. It's what, in fact, gives the proton most of its mass. And that mass scale, you can actually just work out in the theory of strong interactions. It's the Planck scale times e to some exponential factor that depends on how the coupling logarithmically changes over energy scales and the value of the coupling at the fundamental scale. So this is a fabulous way. It's not at all obvious, right? You see two different mass scales that are separated by 19 orders of magnitude in nature. It's not at all obvious that naturalness is satisfied. But what we understand is that, in fact, comes from having one fundamental scale and one coupling that's order 1. And then the natural quantum evolution of that coupling generates a scale 19 orders of magnitude later. OK. So this is a beautiful example. We can understand these scales now consistent with the principles of Dirac naturalness. Another great example we see in nature, I'm sorry all this stuff keeps getting cut off. It's probably, nothing on the bottom is that important, right? Another great example that we see in nature of technical naturalness, again, are the sizes of the couplings of various fermions in the Standard Model to the Higgs. So these we call Yukawa couplings. They tell us how strongly the fermions couple to the Higgs. And also, of course, that gives us an ordering of the hierarchy of their masses once the Higgs gets a vacuum expectation value. So in the Standard Model, there's a large range in the Yukawas. They range over 5 orders of magnitude. And again, it's hard to understand from the perspective of Dirac naturalness why they range this much. But we do know that these hierarchies are technically natural. And that's because in the limit that you take all of the couplings to 0, there's, in fact, an enhanced symmetry of the Standard Model that corresponds to being able to independently rotate all of the fermion fields on their own. All right, so there's a new symmetry when you take the couplings to 0. And that means you can understand why the couplings are not necessarily 1. It's technically natural for them to be small. So we certainly understand from the perspective of technical naturalness why it's OK that the electron is much lighter than the top quark. All right. So in fact, between these two things, either complete Dirac naturalness or technical naturalness, you can make yourself happy about almost all of the parameters that we see in the Standard Model, about all of the couplings of the various fermions and all of the gauge couplings. And you can satisfy yourself that whatever their microscopic origin, our ideas about quantum field theory are compatible with the values of the various couplings we see in the Standard Model. So the natural question to ask, now that we've seen the Higgs, is what happens when we apply the same types of questions to the Higgs? In particular, the Higgs has a mass. All right, we've seen now the mass of the Higgs. It's about 125 GeV. It's related to some underlying dimensionful parameters of the theory. And so you can ask the question, should I be happy with the mass of the Higgs that I see, or should I be concerned that this is actually a violation of our naturalness expectations? All right. So it turns out, so the Higgs is a scalar field. It's the only scalar field, fundamental scalar field we see in the Standard Model. And it turns out that it, in fact, is fundamentally and essentially different from all of the other particles we see in the Standard Model. So for a mass of any other particle, if it's a spin 1/2 particle like a fermion or a spin 1 particle like a gauge boson, in both of those cases, if you have a mass for that particle, when you take the mass to 0, there's an enhanced symmetry of the theory. And so you can understand why that mass can be very small with respect to other scales using this argument of technical naturalness. So it's OK to have light fermions, and it's OK to have light gauge bosons. There's no problem with that. The problem is in the Standard Model, if you add a scalar particle, namely if you add the Higgs, there is no symmetry that becomes manifest when you take its mass to 0. So there's no ability to understand why you could have a small Higgs mass with respect to other fundamental scales, because there's no symmetry that's manifest when you take that mass to 0. So the mass of the Higgs in the Standard Model is neither Dirac natural nor technically natural. And so the question is this a violation of the naturalness principle, or is it a sign that there must be new physics around the corner, some expansion of the Standard Model that helps to place the mass of the Higgs into better context? In exactly the same way as Dirac was unable to understand why the proton was much lighter than the scale of quantum gravity, but we can now understand that because we understand the theory of strong interactions. So the first question you can ask, right, is there's no symmetry that makes the Higgs mass, that makes the theory, when I take the Higgs mass to 0, the theory doesn't become more symmetric. So there's no reason to expect that the Higgs mass should be very different from other fundamental scales, or from other scales at which the theory changes. So one question you could ask, the first naive question you could ask is, OK, I see the Higgs at 125 GeV. If that mass scale is closely connected by quantum corrections to some higher mass scale, what does that mass scale have to be? What is the suggestion of where I should see something new? So working out that argument in detail depends on exactly what something new you mean. But you can come up with a very generic expectation in a quantum field theory, basically by asking, if I imagined cutting off all quantum loops at some energy scale, and I took my low energy theory and I calculated loops up to that scale, what is the answer? What's the contribution that I would get from those loops to the mass of the particle that I see? So you can do that for the Higgs in the Standard Model, and you find that there are a variety of quantum corrections that pull its mass up to be equal to the mass scale at which the theory changes. And basically, it tells you that the mass squared of the Higgs is proportional to the mass squared where the theory changes over a factor of 16 pi squared up to some numerical coefficients. So very naively, right, if the mass scale of the Higgs is being set by some other mass scale, that some other mass scale is within about a factor of 4 pi. It's within about an order of magnitude of the mass of the Higgs itself. Now, you can get more detailed about exactly how precise this relationship is. But basically, the idea is if you have a new mass scale, it's responsible for giving the mass of the Higgs. That new mass scale needs to be below the TeV scale. So the idea then, right, is to look for new particles near the TeV scale. We see the mass of the Higgs should be connected to other fundamental scales. Given the mass that we see for the Higgs, we have a target for what the fundamental scale must be. Now, I want to emphasize this is just a strategy. It's not a no-lose theorem. So unlike what happens if you had a Standard Model without a Higgs, where the theory gets sick as you go to higher and higher energies, nothing badly goes wrong with the Standard Model if there's no new particles at the TeV. It's just you're unable to understand from your fundamental principles why the parameters of the Standard Model are what they are. Now, you might object. You might say, look, OK, we shouldn't hang our hats on this idea. We don't know that it's necessarily a good idea. But the reason why this is such a compelling strategy is we've applied it again and again in the history of our understanding of nature. And it's pretty much always been a beautiful idea. All right. So let me give you just one example of it. So the Higgs is the first fundamental scalar we've seen in nature. But we actually do see other scalar particles in nature. In particular, when the strong interactions grow strong, they combine fermions together to make composite scalar particles. So for example, the charged and neutral pions, these are just bound states made out of quarks. All right, so those are scalars. And so in the theory of strong interactions at low energies, that means we have some scalar particles. And in particular, those scalar particles also get quantum corrections to their mass. And so you can ask the question, given the masses that we see of the pions and their mass splittings, that gives you an expectation for some higher energy scale, right? That naturalness is feeding into that splitting. And now you can ask, do we see new particles at that higher energy scale or not? So to give you a very specific example, if you look at the charged and the neutral pion, those charged and neutral pions, the charged pions talk to photons. The neutral pions don't, by virtue of being neutral. And so that means that there are quantum processes where a charged pion is flying through space, and a photon comes off of it and connects to more fundamental physics and comes back. So that gives you a correction to the charged pion mass that is not present for the scalar mass. And that quantum correction, that's sensitive to arbitrary new scales in the same way that the Higgs mass is sensitive to arbitrary new scales. So you can go ahead and do the calculation. You say, OK, the splitting I predict between the charged pion mass and the neutral pion mass, it's equal to some coupling constants times the new fundamental scale, whatever that is. Now you can go and you can actually measure that mass splitting. Sorry, it's cut off here. So the mass splitting between the charged and neutral pions is 35.5 MeV squared. All right. And that tells you that the new scale, where something new has to happen if this mass splitting is natural, is about 850 MeV. All right. So now you can go in nature, and of course you can look. And before you hit 850 MeV, at 770 MeV, you see the rho meson. All right. So in fact, you see there's a new ingredient of your theory. In fact, when you see the rho meson, that's actually telling you that that's a signal of compositeness in your theory. It's telling you that your scalar is a bound state of some other particles. OK. So this is a beautiful example of the naturalness principle working in nature. You see a mass contribution to some scalar particle. That signals a new scale. You go out and look for that scale in nature, and you see new particles exactly where you expected it. We've been able to run this naturalness argument again and again. So in the case of the charged pion mass splitting, it turned out to be a good idea. It also, in fact, was actually used to successfully predict the mass of the charm quark. So you can go in the kaon system, you can look at the k long and the k short, and you can try to compute the splittings between them. And you'll find that you have a successful prediction for that splitting if there's a new quark in your theory relative to that mass scale, and if that mass of that new quark is around a GeV. So it turns out, of course, this argument was used by Gaillard and Lee to predict the mass of the charm quark, and again was a beautiful example of naturalness working in nature. We've also talked earlier about the proton mass, the sense in which that's natural in the context of Dirac naturalness. So far we have this nice scorecard where every time we see a mass scale that we would like to understand in nature, our naturalness arguments have been the perfect guidepost to understand what has to come next. All right. Yes?
If you find something else another new mass 4 pi away, that would be naturalist problem of its own.
Good. So let me, this now requires a refinement of the argument. So I will now present the refinement of the argument. But before I claim that it's nothing, the naturalness argument is an unbroken string of triumphs, of course, there are other parameters in nature where we have a naturalness expectation, and that naturalness expectation has failed badly. So the canonical example of this is the cosmological constant, which is non-zero. Our naturalness expectations lead us to expect that, at least in local quantum field theory, it should be of the scale of quantum gravity. That is many, many orders of magnitude different from what we see. And as yet, we have no ability to understand this in the language of local quantum field theory. So the measurement of a small cosmological constant appears to be a maximal failure of the naturalness argument. Now, I don't get too discouraged about that because the cosmological constant, this has to do with the fundamental theory of quantum gravity. Quantum gravity is funny. There's mixing of physics at very high energy scales and physics at very low energy scales. So it may be that that helps us to understand more deeply what's going on with the naturalness argument and the cosmological constant. But it's certainly something that should give you pause. It's not as though naturalness has just always been a winner for us. Sometimes we lose. But that makes it interesting every time we have a new naturalness question to ask what the naturalness argument tells us and to see if it succeeds. Okay. In fact, this has been such a successful strategy in the past that the naturalness argument, the question surrounding the naturalness of the Higgs, and looking for new physics around the mass scale of a TeV, this has been a real physics driver at the Large Hadron Collider. So every one of these lines, this is a summary of some analysis done by Atlas or CMS, just in the run 1 data. One day, about a year ago, I counted all of these lines. I think there's 226 of them shown in this summary plot. And if you count them, 170 of the 226 channels are actually tied to searches for particles that you might think are related to the naturalness question of the Higgs mass. So this is just to emphasize, the naturalness strategy is a powerful one. And in fact, it's really the governor of a lot of the searches for new physics that we do at the LHC. But now we can follow up on this question. OK, so we see the Higgs mass. All right, it's connected to some higher scale. So we can guess where that scale might be based on the Higgs mass that we observe. But now we can ask the question, do we actually have a better sense of what might show up at that scale? And the answer is we must, because if it's just some random new physics at a TeV, that actually doesn't help us to explain the mass of the Higgs. The mass of the Higgs is sensitive naively to all higher energy scales, including the scale of quantum gravity. So what we really mean is if there's a new scale that shows up around a TeV, whatever happens at that scale should make the Higgs insensitive to any physics at even higher scales. So whatever happens there can't just be some random junk. It actually has to be something that helps us to explain the Higgs mass being insensitive to much higher scales. So historically, there used to be lots of different possible conjectures for the type of thing that could happen at this scale. Historically, it could be that the Higgs came apart into some quarks of some other confining interactions. Or it could be that the 4 dimensions that we live in open up into an extra dimension. But given what we know now from the LHC, we see the Higgs down to 125 GeV. And we see nothing else. We see nothing else as far as we've been able to look. And we see nothing else in any of the other channels that we've been able to look at. And so that disfavors a lot of possible explanations where something very violent happens to the Higgs when you reach this mass scale of a TeV. And what it leaves us with is a very narrow possibility, which is that something happens at a TeV that expands the standard model to make the Higgs mass technically natural in the same way that, for example, the Yukawa couplings are technically natural, or the masses of fermions or gauge bosons are technically natural. Namely, something has to happen where the standard model is extended into a more symmetric theory. And in that more symmetric theory, if I took the Higgs mass to 0, there would be an enhanced symmetry. All right? If that happens at a TeV, then we can understand why the Higgs mass is what it is, and why that mass is insensitive to physics at vastly higher scales. Okay. So that gives you a very specific set of expectations for what should go on. And since we're in the game of trying to come up with predictions for things to look for at the LHC, specific expectations are useful. So it turns out, at least in a four-dimensional quantum field theory, Coleman and Mandula and Haag, Sonius, and Lopuszanski, they actually enumerated all of the possible things that could happen consistent with an interacting quantum field theory. And there's basically just two possible things. So one thing that could happen is that the standard model is embedded into a more symmetric theory that exemplifies supersymmetry. So this is a fundamental space-time symmetry that relates bosons to fermions. All right. The other possibility is the standard model could be enlarged to have a larger set of global symmetries, which is to say that there are extra particles where if I mix them all together with symmetry transformations, the theory would be invariant into those transformations. And those are basically the two options for symmetries that we could have that we could extend to act on the standard model. And both of them have to work in basically the same way. So supersymmetry or this global symmetry might be the fundamental symmetry of our theory above a TeV scale. But we don't see all the new things predicted by these symmetries down in the standard model. So the symmetry has to be broken in some way. And when that symmetry is broken, that gives mass to all of the new particles associated with the symmetry. So at very fundamental scales, at short distances, there's a new symmetry. At some scale, that symmetry is broken. That gives us a prediction that there's new particles at that mass scale. And those new particles now give a contribution to the Higgs mass that we can go ahead and calculate. And this expectation for where the scale is tells us these new particles have to be around a TeV. So you might think there are lots of ways to explain why the Higgs is light, but at the end of the day, there's really not that many options. And so that gives you a very focused set of ideas to look for what might be evidence for naturalness of the Higgs in nature. So something that I just want to emphasize is both of these symmetries, whether it's supersymmetry that protects the Higgs or global symmetry that protects the Higgs, both of these are continuous symmetries, and in some sense, they commute with the standard model interactions. So that is to say, if I enhance the standard model to have new particles so that the theory becomes more symmetric, these new particles, they are also charged into the standard model forces in a way that's dictated by the symmetry structure. So these new symmetries predict new particles, but these new particles are charged into the standard model. So there are new particles that are charged into the strong interactions, new particles charged into the weak interactions, new particles charged under electromagnetism. And their charges under the standard model forces are dictated by the symmetry structure of the theory. So it's very, very predictive. At the end of the day, this gives us a very, very sharp strategy for looking at new physics at the LHC. Basically, either the standard model is completed into supersymmetry, or it's completed into a global symmetry. In both of those cases, you predict a spectrum of new particles. They can't be too heavy, otherwise the Higgs mass would be unnatural. And so that means that you have an expectation for how close to the Higgs they're going to be. They all have different quantum numbers under the standard model, but some of them at the very least are charged under the strong interactions. And if you have the world's greatest proton-proton collider, it's a real simple game at that point. If you predict new particles underneath the TeV that are charged under the strong interactions, you should be able to produce them by smashing together protons together at high enough energies. So that's the game at the LHC. All right, we have the world's most powerful proton-proton machine. We require that these new particles be there. We require some of them to be charged under the standard model, the standard model interactions. So now we just need to go and look. So my experimental colleagues have been doing an extraordinary job of doing these searches over the lifetime of the LHC. And what it's led to, of course, it's led to the discovery of the Higgs and the non-discovery of anything else. So I like to call this the missing partner problem. Right? We have these strong arguments for why we expect new particles. We don't see them. And that's in tension with our expectations from naturalness. So this is just one of many summary plots. This is the Atlas summary plot of searches for partners predicted by supersymmetry. And if you can read the x-axis, this is the mass scale. This line here is about a TeV. And all of these are exclusions for various different types of particles. And what you see is, OK, it varies from search to search and particle to particle. But for the most part, our exclusion limits are now starting to push above the TeV scale. So we had this very strong set of expectations for what we needed to see based on naturalness arguments. We've gone and we've looked for those particles, and we haven't seen them. So there's two possibilities, right? One is that somehow we're fundamentally wrong about our expectations about how naturalness works. Maybe the Higgs mass is like the cosmological constant problem, and this whole thing has been a red herring. But the other possibility is that we just haven't thought hard enough. Okay. So the other possibility is that there could be room for other ways of making the Higgs natural that are consistent with our expectations of naturalness. But for one reason or another, maybe we just haven't thought about them yet. All right. Now, it's a little hard, the way that I've constructed the argument, it's a little hard to imagine what those possibilities might be, right? We had this very narrow set of arguments. We have to have new physics. It has to be a symmetry in order to explain seeing a light Higgs. That symmetry commutes with the standard model, so it has to have new particles charged in the standard model. We look for them, we don't see them, we're in trouble, right? But it's worth asking, at what point in that flow of logic could the logic actually break? And could it be possible for the Higgs mass to still be natural, but there be a fundamental reason why we haven't seen that evidence yet? Okay. So the direction that I've been pursuing over the last few years is to take at heart the idea that symmetries somehow explain the lightness of the Higgs, but to recognize there's more to the universe than just continuous symmetries, right? There's more to the universe than symmetries under continuous smooth transformations of objects. In particular, something that chemists knew well before physicists, there are discrete symmetries of nature. For example, there are symmetries of crystals, where it's not symmetric under continuous rotations, but it's symmetric under discrete rotations. All right. So you might ask yourself, OK, how far could I get with discrete symmetries? What would the fantasy be? Well, the fantasy would be that it would work in exactly the same way as continuous symmetries, except instead of having a continuous fundamental symmetry, it's just a discrete fundamental symmetry. So at very short distances, the standard model is part of a much more symmetric theory, but that symmetry is a discrete symmetry, exchanging different components of the theory. That symmetry is broken at some scale. That gives new particles. Those new particles help to explain why the Higgs mass is where it is. But the key difference relative to the continuous symmetries is that in some sense, discrete symmetries don't commute with the standard model gauge interactions. So if I have a discrete symmetry that relates the standard model, say, to another copy of the standard model, we have our standard model forces. They have their standard model forces. So all of the new particles that are predicted by this discrete symmetry, they're not produced through standard model forces. They don't talk to our forces. And so when we smash protons together, we don't have any expectation for producing them abundantly. All right. So this is just a fantasy, right? It sounds like a good idea. So the question is, can you actually make it into a realistic theory that satisfies all the criteria we have for a natural theory? And can you see how this would actually work? So it turns out the first example of this predated by quite a bit my interest in the field. It was a proof of principle that was actually written down in 2005 by these authors. This is Roni Harnack here, who's been twinned. They called it the twin Higgs. They wrote down the theory not because they were trying to understand LHC data. At that time, the LHC, of course, wasn't running. But they just wanted to know, is it possible to write down a theory where you have a discrete fundamental symmetry, and that discrete fundamental symmetry makes parameters technically natural in the same way that we think continuous symmetries do? So their fundamental symmetry was to say, well, what happens if we have our standard model and a different copy of the standard model, and we just exchange them by a mirror symmetry that swaps our standard model with that standard model? This is actually an old idea that even much predates these authors. People who are trying to understand the violation of parity symmetry in the standard model have long conjectured the existence of a mirror symmetry that exchanges the standard model with a different copy so that the two combined copies do, in fact, respect parity. But the key ingredient here was to ask, can that discrete exchange symmetry, swapping two copies of the standard model, can that be used to explain why the Higgs mass is light? OK, so the cartoon picture of the way this works, I won't bore you with the detailed field theory, but the cartoon picture is you just have your copy of the standard model, which you know and love. It's all the things that you're made out of. And there's a mirror copy of the standard model. And the only thing that connects them is there's a Higgs field that lives in our standard model, and there's a Higgs field in the mirror copy. And those two fields have a strong interaction connecting them. And otherwise, these two copies are completely symmetric about exchanging one copy for the other. OK. So the key for how this helps you to explain the naturalness of the Higgs has to do with these interactions of the two Higgses. The short version of it for the aficionados is, although there's just a discrete symmetry exchanging the two Higgses, at the level of quantum corrections to mass parameters, a discrete symmetry actually gets enhanced to an accidental continuous symmetry. So if you could use a continuous symmetry to explain why the Higgs mass is natural, you can still do it with a discrete symmetry up to some conditions. All right. But that's a powerful idea, because it tells you now that you can explain why the Higgs mass is small without introducing lots of new particles charged under the standard model. You introduce particles that are charged under somebody else's standard model. So they have their own strong interactions, their own weak interactions, but those have nothing to do with us. If you'd like to sort of come up with a simple graphical cartoon for what's going on, all of the traditional theories, all of our traditional solutions to the hierarchy problem, they had the form of the Higgs talking to the standard model, and that being related by a continuous symmetry to lots of new particles that were also charged under the standard model. So the simple idea of using discrete symmetries is now, instead of having a whole bunch of new particles charged into the standard model, the discrete symmetry relates the standard model to some other copies of it, and those new particles are not charged under our forces. Okay. So you can work out the details. You still predict a new spectrum of particles, but these particles have very different quantum numbers from the things that we see in the standard model. So where the particles have to be, namely living around the TeV scale, that's still true, all right? But the quantum numbers of those particles that explain the lightness of the Higgs, they're completely different. And they have nothing to do with standard model quantum numbers. So it turns out you can actually write down many theories of this form. The first one was this one with an exact mirror symmetry relating the standard model to another copy.
So the two Higgses are related by, so they're not scalars.
They're scalars. They're related by a Z2 exchange symmetry. So they still, in terms of the Lorentz symmetry, they're still scalars, right? But you can group them into a multiplet by their relation through the Z2 transformation. There's, in fact, a further technical restriction that the potential involving the two scalars themselves has to be SU4 symmetric. But I'd be happy to tell you more about that afterwards. That's a.
Because it seems like if a scalar, you're coupled to all the other guys, right?
Well, but the point is that so now you still have the gauge symmetries of the standard model and this other standard model. And so as we know in the standard model, once you have the gauge symmetries, there's a finite number of interactions you can write down consistent with the gauge interactions. So if you take two copies of the standard model and you enforce that the theory be symmetric under the exchange of the two copies, you don't get any other mixtures, all right?
No, I'm talking about Higgs itself, because it's a scalar.
So yes, but it's charged under its own copy of the electroweak interactions. So it can't couple to any of our electroweak interactions because that's not gauge invariant. Okay. So gauge invariance in the Z2 symmetry factorizes these two sectors. All right. And that's a compelling realization. All right. So the basic story, all right, so the simplest model you can write down, there's an exact mirror symmetry. What we've understood in the last few years is there are many more interesting realizations of this idea, where basically there can be exact or approximate discrete symmetries that relate the standard model to some mirror copies. And it's those particles not charged into the standard model that help us to explain why the Higgs mass is light. So where this gets interesting is if this is what's happening in the universe, all right, it's then easy to understand why we haven't seen anything at the LHC. Because the LHC, we've been smashing protons together. These particles are not charged under our strong interactions, so they're not produced in proton-proton collisions. So the fact that we have null results in lots of our searches is very compatible with this idea. But now you have to ask yourself, we're not in the getting around search limits game. Well, some of us are. We try not to be in the getting around search limits game. We're in the trying to write down theories of nature and make predictions game. So if this is what's going on, the real question is, how can we find this either at the LHC or at other experiments? So the first thing you might naturally ask is, well, let's do some version of what we already do at the LHC. Let's try to produce these new particles directly. But the problem is the only way they couple to us is through the Higgs, because our Higgs talks to that Higgs talks to those particles. Okay? So there's a very small coupling between the Higgs we've seen and these new particles. That's the only portal between that sector and our sector. And so if you ask at the LHC what sort of processes might produce these new particles, they only get produced through a virtual Higgs boson, and the rate for that process is vanishingly small. So if you want to play the game that we normally do of colliding protons together, producing these new particles directly, you're pretty much out of luck. It turns out there are two ways that we can start to try to make sense of this and make further progress at the LHC. One of them is actually by studying the Higgs that we've seen more precisely than ever. Now, you might have concluded we've studied the Higgs so far. We know it agrees with the standard model predictions to within about 20%. Maybe that's good enough. Maybe we go home. It's probably the standard model Higgs. But what you expect in these theories is that the Higgs that we've seen, it's not exactly the standard model Higgs. The actual mass eigenstate that we see is mostly the standard model Higgs and a little bit the Higgs coming from this other sector. And if that's the case, there's some mixing between these two Higgses. That means that changes all the properties of the Higgs boson by amount proportional to the mixing. So the natural size of this mixing is something on the order of about 10%. And we know the Higgs properties to about 20%. So there's a target. There's a target which is to measure the Higgs properties more precisely, to get down beneath about the 10% level. And when you get to that precision, the prediction is you should start to see deviations from the standard model. You should start to see that all of the couplings of the Higgs to standard model particles are dialed down by about 10% from what you would have expected from the standard model. So right now, this is consistent with everything we know at the LHC, but it's just within reach of the precision that we would get with Higgs measurements in the long lifespan of the rest of the LHC. So this makes it really worth paying attention to what else we can learn about the Higgs as we continue to make measurements at the LHC in the coming decade. The other handle we have is a bit more exotic and a lot more exciting. Which is that there is, so there is actually a way to produce particles in that sector and have them come back to us in a way that we could see in LHC detectors. So the reasoning behind this is a little subtle, and I'll try to break it down for you. If we have a discrete symmetry that's explaining why the Higgs is light, that predicts new sectors, and they have their own copy of the strong interactions. So just as our strong interactions, just as the QCD interactions grow strong and confine just beneath the GeV scale, the strong interactions of these other sectors should also grow strong and confine. And they should also generate a spectrum of particles that are bound states of their strong interactions, just as our QCD generates pions and kaons. But something very interesting can happen depending on the spectrum of fermions in these other theories. If we took QCD and we took away the light quarks, we took away the up quark and the down quark and the strange quark, what we would find when QCD confined is not that mesons were at the bottom of the spectrum, as we see. We would actually find that the lightest states were bound states of the gluons. We would actually find that the lightest states were things that we call glue balls. Now, we don't see those abundantly in QCD because we do have these light quarks. And so although the glue balls are probably there, they decay very quickly to lighter states. But if through these discrete symmetries you have other strong interactions where those quarks aren't quite as light, then the particle at the bottom of the confined spectrum of their copy of the strong interactions can be these glue balls. And these glue balls are pretty awesome because they have lots of interesting different angular and charge parity quantum numbers. And in particular, we actually know from studies of the lattice that the lightest such glue balls have exactly the same quantum numbers as the Higgs boson. All right, they're scalar particles with CP quantum numbers ++. OK. Now, generically, in a quantum field theory, totalitarian principle tells you everything not forbidden is compulsory. If I have two particles with the same quantum numbers, in general, they'll mix. So you might hope that this is a way that the Higgs might mix with these new particles. But in fact, it's more robust than that. The discrete symmetries in these theories that make the Higgs natural, they actually force upon you a coupling that gives you a mixing between the Higgs and these glue balls. And the coupling, in fact, you can go ahead and compute in a given theory. So you can actually calculate the size of the mixing. And it leads to a very interesting effect. All right. So the effect is the following. In the standard model, we produce the standard model Higgs. And at about 1 decay in 10 of the standard model Higgs, it actually goes to pairs of gluons, all right, the mediators of the strong interactions in the standard model. In the presence of these new couplings required by the discrete symmetry, much more infrequently, about 1 part in 100 to 1 part in 1,000, it actually goes not to our gluons, but to the gluons of this other sector that's related by discrete symmetry. And those gluons, then they hadronize, they form glue balls, they form these states in their spectrum. So that's a way that tells you every once in a while, when we produce a Higgs, very rarely, we produce these new particles that are bound states of the strong interactions in the new sector. But because these states also have a mixing with the Higgs, it's a very, very small mixing, but it's there, and you can calculate it, they eventually will decay back to us, all right, because we have lighter particles in the standard model than they do. So you can go ahead and you can calculate the decay rate. And it turns out it's quite long. It's too long to be a prompt decay. But in fact, when you produce these particles, what happens is they come back to the standard model on a length scale that's about the size of the LHC detectors. So the LHC detector is about 10 meters, loosely speaking. What that tells you is about every 100 or every 1,000 times you produce a Higgs at the LHC, it decays into this other sector. And then the states that you produce in the other sector, they come back to us, but they take their time. And so when they come back to us, they've traveled some macroscopic distance in the LHC detectors. And so that decay happens somewhere in the volume of the detector. So instead of smashing protons together and getting a shower of events at the center of the detector, you smash protons together, you get some stuff there. And then a moment later, you get something elsewhere in your detector, corresponding to the decay of one of these hidden sector particles coming back to the standard model. All right. So that's a spectacular signature. All right. It's very different from what we thought we might be looking for when we built the LHC detectors. But it's one that we can look for by being sufficiently clever. And because it's a very spectacular signature, you only need a few events of this sort to know that something interesting is going on. So it's been an interesting amount of progress for both ATLAS and CMS to figure out how they can use their detectors to be sensitive to these displaced decays. So that's just because the detectors, when they were originally constructed, were constructed to understand physics that was promptly produced in a proton collision. But both ATLAS and CMS have been extremely clever about it. So ATLAS has understood that they can pick up events where they see something appearing later in the detector and nothing coming in from the original collision. And they can basically make measurements of energy deposition at various places in the detector and see that there was something that showed up in the detector away from the original interaction. CMS can do something very different that's also equally cool. So CMS has a fabulous tracker right around the collision point. And if you have one of these displaced decays happening relatively close to your original interaction, you can actually directly see the vertex. You can see particles coming out of a vertex that doesn't come all the way back to the interaction point. So both of these are very powerful tools. It's taken a fair bit of work to apply them strategically to look for these processes. Right now, the answer is doing searches for these displaced decays at the LHC is not enough to meaningfully constrain these theories. But if we push on it hard enough during the rest of the LHC run 2 and throughout the remaining lifetime of the LHC, we should be able to make significant progress either in discovering these theories if they're there or in ruling out a lot of the motivated parameter space. But the key point is it's pushing us in new directions. It's giving us new observables and new measurements to make at the LHC. We don't have to despair at the null results we have so far, but instead we can look in interesting new directions. Something else that it's been doing is starting to push people to think about new experiments, either ones that are parasitically related to the LHC or experiments that might follow after the LHC itself. So I really like this quote from Benjamin Franklin. We are, I think, in the right road of improvement, for we are making experiments. As a theorist, I think that's a concession that I'm not the one doing the serious work. So what are some of the experiments? Well, these are not my experiments. They're experiments that are being proposed and developed by a lot of brave people. One of them is a beautiful idea. The acronym is Methuselah. And the idea is to make an experiment that would be parasitic on the LHC. So we already have the LHC. It's a fantastic machine. We have these fantastic detectors. And what if we can, instead of looking at events happening in the detectors themselves, what if we can go buy a farmer's field somewhere in France and put a detector above one of the LHC detectors? So the LHC detectors, of course, are deep underground. What if we can pave the farmer's field above the detector and put a football field, a scintillator on top of it? OK, so why is that an interesting idea? Apart from, I don't know, pissing off some French farmers. It's that if you produce these particles, so I said typically if you produce these new particles in the sectors related by discrete symmetries, they can come back to you on the LHC length scale. But as you go through the parameter space of these theories, more often than not, they come to you a little bit later or a little bit larger than the LHC length scale. So if you're able to build a detector that's up at the surface, so about 100 meters away from the interaction point in the LHC detectors, and instrument that with scintillators, then you could become very sensitive to these particles that are being produced in LHC collisions, travel some macroscopic distance before decaying. All right. So this is a beautiful idea. And in fact, it can probe a lot more of the parameter space than the LHC collaborations themselves can. So this is a beautiful example of really trying to, now that we know that we're in the game of looking for particles that are somewhat long-lived and produced abundantly at the LHC, this is a great way to try to start pinning them down. I think the other direction that's really promising is part of the game is just to study the Higgs as much as we can, right? We know that we'll learn something by making precise measurements of Higgs properties. We also know something that very rarely the Higgs has these exotic decays. So the best thing we can do is build Higgs factories to probe those couplings as sharply as we can. So there are a lot of proposals that are on the market now, either for building future circular electron-positron colliders or future linear electron-positron colliders. But both of these things would be machines that could be decisive in pinning down theories of this type. So there's been a lot of progress in the last few years in this line of thinking, but I think there's a lot more room to explore. I've focused on some of the interesting things that happen at the LHC, if this is what's going on. But you can imagine if your prediction is there are new sectors that are neutral under the standard model, but coupled to us through the Higgs, that could have very interesting implications for dark matter. There could be a lot of very natural dark matter candidates embedded in these theories. Another thing could be that these theories typically predict additional sectors with very light particles. And we know, of course, if those sectors are in thermal equilibrium with us in the early universe, we produce lots of those particles. They contribute to the energy density of the universe. And we should actually see evidence of that when we look at in the CMB. So future improvements that we can make in measurements of dark radiation and neutrino masses could also be a way of getting a handle on these ideas. So there's been a lot of progress in recent years. There's a lot more room to explore. And I think it's an exciting and fun time to be in the game of just asking, what classes of theories have we missed? If we take the naturalness strategy seriously, are there places we haven't been looking that give us something new to be excited about? Before I close, I just want to mention that's not the only possible game you could play. So the strategy that I've taken is to say, symmetries seem like a good solution to the naturalness problem. Let's just try to find a different symmetry. But you could also say, I don't like symmetries. Symmetries haven't done anything for me. I like dynamics. Maybe it's possible that something happening in the early universe actually put me in a vacuum or a minimum of my potential where the Higgs looks natural, even if the fundamental parameters are much larger. So maybe there's a way to dynamically explain why the Higgs mass is what it is, even if the naturalness arguments tell us it should be much larger. So in the last couple of years, there's also been remarkable progress in this direction. It's, in some sense, a thornier problem, because understanding in detail how fields evolve in the early universe to make this work is a lot harder. But people have made great progress. I don't want to bore you with the details, and some of the details are now here obscured. But the basic idea is you can, in fact, explain the smallness of the Higgs mass if it's scanning as the result of the evolution of some other field in the early universe. And if you can explain why that field stops in a special place, where its expectation value is giving a contribution to the Higgs mass, then you can explain why the Higgs mass value is what it is. So these ideas have also gained a lot of enthusiasm in the last few years, and I think we're only in the early days of understanding how far we can go. So that's just to give you a sense of the flavor of what's going on. We've pushed our old historical ideas to their limits. We haven't seen evidence for them yet so far at the LHC. At this point, it could either be a sign that the naturalness argument itself is failing, or it could just be a sign that we haven't been creative enough, and there are ideas out there that actually point us in the right way. So I think thinking about discrete symmetries is a great version of it. Thinking about dynamical selection of our modern-day vacuum is a great idea. But there's probably lots of other ideas out there that I'm certainly too old and slow to think about, and many of you young people in the audience are probably ideally primed to discover. So with that, I just want to bring things to a close. Naturalness, hopefully as I've convinced you, has been a very compelling argument for understanding the features of quantum field theory. The Higgs discovery, of course, it's a triumph in that it marks the completion of the standard model, but it also brings us a new puzzle because there's now a parameter that we can't understand from naturalness arguments. The naturalness strategy, if we apply it like we always have, it's a very compelling pointer. It tells us we should expect new particles near the weak scale. And we already have a very robust program of looking for evidence of those particles at the LHC. But the thing that I want to emphasize for you today is much of what we've been looking for so far fits into a few classes of ideas that we've had a lot of time to think about. There are new ideas that are coming on the market in the last few years, motivated by null results at the LHC. Some of them include, for example, thinking about different symmetries like discrete symmetries. Some of them are motivated by thinking about dynamics. But really, we're in very early days, so there's a lot more in this program. There's a lot more thinking we can do about the naturalness argument and how it interacts with the physics of the weak scale. So it's an exciting time, and I hope some of you find it interesting moving forward. So I leave it to you to decide. We have all these successes of naturalness in nature we've seen so far. We have apparent failures like the cosmological constant. I think the jury is still out on the Higgs mass. Whether or not you think the Higgs mass is natural or not, hopefully at least by the end of today, you agree that it is an interesting question to ask whether nature is in fact natural. Thanks very much.
Nathaniel, we have time for a few questions.
So for the cosmological constant, you already put the marker over there.
It's not natural by the rules of local quantum field theory, right? If it were natural by the rules of local quantum field theory, we would have discovered supersymmetry at the EV scale. And we wouldn't be talking about it, yeah, because we couldn't then make, macroscopic bound states. Right?
Would another approach be to try and measure very accurately the invisible Higgs branching fraction?
Yes, the invisible Higgs branching fraction. In addition, so basically, the size of corrections to Higgs couplings and the Higgs invisible branching fraction are approximately the same. So I've really zoomed in on the Higgs couple. Well, so there are ways to turn off the Higgs invisible branching fraction or to reduce it, because that's sensitive not just to the couplings, but to kinematics, right? It depends on the detailed masses of the particles in these new sectors, whereas the changes in the Higgs couplings is only sensitive to the couplings themselves. So you could end up in a situation where there's no Higgs invisible decay, but there are deviations in Higgs couplings. Although I would say, indeed, the generic expectation is Higgs invisible decays and Higgs coupling deviations are comparable in size. But if you just look at where we are right now, we know Higgs couplings to about 20%. Higgs invisible, we know to about 30%. Now, the couplings comes because Atlas got lucky, and the Higgs invisible is not better because CMS got a little unlucky. So maybe these things would converge in the future. But absolutely, that's another very productive avenue.
What would be, presumably, all these dark sector, right? Which is like a hidden sector.
Yes, absolutely.
Exactly the same.
Yep.
But a completely different set of internal physics
Yep.
in there.
Yep.
So then the differences would be in qualitative numbers. So there's
Good. So obviously the path from signatures in a collider to reconstructing the microscopic theories we know is complicated. But yes, there are various things. For example, the multiplicity of the particles that you produce, the mass scale associated with them, the kinematic distributions of the decay products. All of those things you can use to start walking back to reconstruct the way in which the standard model Higgs talk to Nu's degrees of freedom. And you can use, based on multiplicity and kinematic distributions, you can start to figure out what were the quantum numbers of the things that were involved. So it's a much more, it would be great if we ended up in a situation like we did in the early days of the standard model, where, for example, we had lots of strong resonances and we had to make sense of the underlying theory, right? It's a much harder game when those particles are not prompt in your detector, but are instead decaying at some length. But you can certainly imagine, if you gather the same type of information that we gathered, for example, from the strong interactions, that you could find compelling evidence for, at the very least, the size of the non-abelian gauge theory, right? So you could start. Yeah. Absolutely. So for example, if you have, so you could ask the question, is it SU3 or SU4? Like, what is the strong gauge group? So the good news is, right, as you change the size of your non-abelian theory, the spectrum of glue balls changes. All right, so there's always the 0 plus plus at the bottom, but now you have the 0 minus plus, you have the 2 plus plus, you have all the JCP quantum numbers that you can possibly generate. So generally what happens is, when you go into the sector through the Higgs, you don't just make the 0 plus plus. You make whichever, you make lots of ones depending on, okay, so now you reconstruct the spectrum of glue balls based on the cascades that hang down to the standard model. And based on that, you could, for example, start to find evidence for the size of the non-abelian group whose bound states were giving you this result. Okay. Yeah.
And also this dark sector, this SM prime, it's not coupling to the standard model, but gravity is not part of the standard model. So it could clearly couple to gravity. It could be dark matter.
Yeah, so in fact, there are lots of great dark matter candidates.
We would have a lot of difficulty ever finding it.
No, because the answer is because we couple through, the Higgs does talk to these things. So the Higgs coupling has to be there. And so for example, in the standard model, so baryons are great. This other sector has stable baryons. So baryons could be the dark matter candidate, and their abundance could be related to the baryon asymmetry of the standard model. So that's something that could happen. And you would see them because they couple to us through this very small coupling with the Higgs. Exactly. Something else that could happen is the leptons of these sectors could actually be dark matter. A standard statement. So when I said global symmetry, so really what I mean by global symmetry, okay, so you could ask, all right, maybe the Higgs is just a bound state of some other confining theory, right? Now, the only way to reconcile that with the mass gap between the Higgs and the fact that we haven't seen anything else is if the Higgs is also a pseudo-Goldstone boson, right? So that narrows you down to composite Higgs theories, but in particular, if it's a pseudo-Goldstone boson, that means the essential thing that was protecting the Higgs was the global symmetry, right? If the Higgs is a pseudo-Goldstone, it's the global symmetry, and then compositeness just gives you the UV completion at the multi-TeV scale. So the statement right now about composite Higgs, there's two things that you use to get a handle on composite Higgs. One is you look for the fermionic top partners. So null results in the search for fermionic top partners place the same strain on composite Higgs models that null results in searches for scalar top partners place on supersymmetry. All right. There's also then Higgs coupling deviations that you expect in composite Higgs models. All right. And those, I would say right now, those are not substantially stressing the naturalness of the model relative to these null results in searches for top partners. Great. Thank you very much.